the technical challenges. There are three main technical challenges: synchronous to asynchronous generation technologies, and new RE, intermittent and variable by nature. Another thing is most new renewable energies are distributed power sources. And there are non-technical challenges. Under this, I talk about the financial challenges and implementation challenges. Right. First technical challenge, I will talk on renewable energies are asynchronous generation. In synchronous generation, the grid interface is a rotating generator. But in asynchronous generation, grid interface is an inverter. Solar power plants, you know that even in DC power, the DC power is converted to AC by an inverter. Then grid interface is an inverter. In all the wind power plants, modern wind power plants, so the synchronous generation, when this asynchronous generation share of the system is high, that you learn that the system inertia goes down. Because the system inertia, we need the rotating generators to supply system inertia. Then there will be some difficulties in primary regulation, because primary regulation support is given by rotating generators, and difficulties in secondary regulation as well, and difficulties in supply demand balancing. And also that all these result to system stability goes down. So that is one challenge. Then you see, you know that what is H constant now. In large hydro generators, the H constant, it is given by seconds. So in simple terms, H constant is how long a particular generator or a system can maintain a constant speed, or in a system, if we talk about, when we talk about a system, how long it can maintain a constant frequency by its stored kinetic energy. In a large hydro generator, the inertia constant is in between 3 to 6 seconds. In Victoria, for an example, so Victoria 3.45, New Lakshapan 3.3. When the generator is bigger, the inertia bigger, and the speed is more. It's rotating in high speed, the inertia is more. So you all know better than me about those equations and those principles. In thermal generation, the coal power plant and gas turbines, the inertia vary between 4 to 9 seconds. In gas turbines, we have gas turbines in Kaltissa. The coal power plant inertia is 4.38. In a 110 megawatt gas turbine in Kaltissa power plant, it is about 7 seconds. So gas turbines inertia is more. So we have 3 gas turbines, 110 megawatt gas turbines. We have 2 combined cycle power plants. In combined cycle power plants, we have gas turbine and steam turbine both. But the gas turbines have inertia because we use gas turbines, but the response time is also quicker. In wind turbines, you see, it's very low, often low. In modern wind turbines, the grid interface is an inverter. It's very close to 0. In solar power plants, the inertia is 0. It doesn't give inertia support. So let's move to this is actual curve of a 100 megawatt wind power plant in MENA. We have a 100 megawatt wind power plant in MENA. This is a 3-hour duration, the wind speed variation, not the wind speed variation. This shows how the energy, instantaneous power output of that wind park is varied because of the variation of wind power. When this control has to adjust the others to balance the supply and demand. So it's a challenge. So next, you see the wind, if you take wind is also seasonal. This is the wind speed change in a year. In a monsoon, generally from April, May to September, October, we have, it's a monsoon, so we have more wind. In intermonsoons and other time, the wind velocity is low. The wind generation is also goes down. Then this is a daily variation of wind pattern in Mana in a particular day. So it is variable. This show the solar generation. In left side, it's in the perfect, we'll have a curve like this. So actually, so in the solar system, the generation curve is like this in the what you see in the right side. So you can see if you have a solar system in your home. So go to the web, go to the app you are using, and you can see this curve. So wind, so start to generate at about 6, 7 o'clock, and it's go to peak at about 12 noon, and it comes down and comes to zero at about 5, 6 o'clock in the evening. So this curve, very important. So we have a solar target. So we have a target to go to 70% renewable energy in 2030. If you to go to that target, we should have to get add about 3,000 megawatts of solar power plants to system. If we add 3,000 megawatts of solar power plants, so the peak power will close to about 2,000 megawatts at about 12 noon. So the solar power plant alone can't run the system. If it is a windy day, you will get other renewable energies like wind as well. And also to maintain the system inertia, so primary regulation and secondary regulation. So we should have some firm energy power plants as well. With all these, the minimum, the peak value will goes up to about 3,500 megawatts. But you know that the maximum demand of our system at night time also it will 1,000 megawatts, 2,800 megawatt like value. In daytime, it is less than that. That is about 2,000 megawatt. But with this solar addition, total generation will be about 3,500 megawatts. So definitely there will be curtailments, and we should have storage, pump storage, and battery energy storage. So this show you this is a very important graph, combination of graphs. So actually, this is in our approved generation plan. I received this from our planning engineers. I must thank to them. So this is a public document, actually, not confidential documents. So this is in approved generation plan. So you see, if we go to the renewable targets in 2020, 2030, 70% renewable energy target, with that share of renewable energies and with base load power plants. In the dry season, we generally call from January to April, dry season. So then May to September, the middle one, is generally high wind season. And then October to December, we call wet season. But in this monsoon time, in high wind season, we get rainfall, but in after about September to October, all our reservoirs are filled if we have enough rainfall in that particular year. So this show the generation curves of general generation curves of in different seasons. So you can see in the dry season, we have more and more solar energy. So you can see some negative loads here in some color, ash color. They are battery and power in up to 2030, we don't get pump storage. They are battery energy storage systems. We expect to get add some battery energy storage. This negative power, we can say negative generation are battery energy storage. With all these energy storages, still this red colored power curtailments are there. We have excess power. So you can see in the first one, in the dry season, the right corner one, it's a Sunday. In sunny Sunday, there are a lot of curtailments. These red colored ones are curtailments. In windy season, we have a lot of wind. To go to this target, presently we have about 300 megawatt of winds, but we have to go to about 1,200 megawatts of wind to achieve this target. It's a challenge anyway. Let's discuss the challenges. But so we should go to this. In wind season also, there are curtailments because of high wind. You can see that the green colored, in this, the green colored share is more. And this is wet season. Right, let's go to next slide. Our other technical challenges, the most of renewable energies are distributed sources. We call the distributed and embedded generation, right? So in conventional power plants, in conventional system, so you know that power plant are in geographically concentrated. Large synchronous generators are in large power plants. So Laksapani, Victoria, Canal like power plants. So those are connected to the transmission network. Then that power come to the grid substations via this transmission network. Then we use medium voltage network here, 33 kV, 11 kV. Then it comes to the homes. Then power plant to the transmission network, then medium voltage system, and to the consumers. The load flow, you can see these red arrows, the load flow is happen to single direction from generation to the loads. But in the present day's grid, you can see we have large power plants. So conventional power plants plus the renewable power plants. The Mana power plant, 100 megawatt Mana power plant is connected to transmission network. And there are solar parks also. In addition to them, there are power plants connected to the 30 kV and 1 kV medium voltage system there. And also there are rooftop power plants. We call it rooftop solar in your homes at the customer end as well. Then you see the power flow happen to both directions, from upwards to downwards and from upwards. So this is called the distributed generation, effect of distributed generation. Then you see, because of the principles of system controlling, demand and supply balancing, it is a challenge. We talk about some invisible generation because of the embedded generation, distributed generation. In this diagram, you see, in this particular moment, consider that in this feeder there are 10 megawatts consumption. In other feeder, another 10 megawatt. Total is 20 megawatt. So 20 megawatt is fed from the transmission network. This is what the National System Control Center see. The National System kV level and some parts of 30 kV level. So consider there is a distributed power plant connected to this 30 kV network. So then now this power plant to generate power. Now think this is generating 5 megawatt. Then that earlier there was a 10 megawatt demand here. Now still the 10 megawatt demand is here, but only 5 megawatt is fed by transmission network. The other 5 megawatt is balanced from here. So the transmission system, and at the transmission level, the system control center see only 15 megawatt. But actual power consumption is 20 megawatt here. So this is the invisible generation. We call this invisible generation because of distributed embedded generation. Right, this is what I showed you at the beginning. This is a generation curve of a Sunday. So I said you, this is not the actual generation curve, but this is what the transmission network or the system operator see as the generation curve or demand curve, because there's an invisible generation, huge amount of invisible generation here. So this is there in weekdays and working days also, but because of in a Sunday, the demand goes down, we can't reduce the invisible solar supply, but what we can do is the system operator has to reduce the other power plants. Then this is the invisible rooftop solar, and this is the share of firm energy power plants. So this is actually, though we talk about sunny Sunday, the topic is sunny Sunday. This is not happening only in Sundays. So today also our system control center deputy general manager talked with me. So he's telling this issue is there in Saturdays also, and also in public holidays. Whenever system demand goes down, problem is there. Because of this initiable solar, and you can see others, this green colored ones are wind power, and this light blue colored are the mini hydros. Then this dark blue are hydros, and this you can see the large hydropower plants, and also the coal power plant load has reduced, and a lot of other power plants has switched off. So share of firm energy which support to inertia and primary regulation, second regulation is only given by this portion. So because of this, the inertia of the system goes down, and that will cause to system instability. And a monkey can trip that system. But that problem has almost solved by our talented system control engineers. So I will explain you how they have done it. So our management has taken some decisions, but those decisions has a cost. So let's discuss those things in next slides. I will move to my next slide. This is a very interesting one. You see, in CB, we have 7 million consumers. Out of 7 million consumers, the rooftop solar has only 120,000 consumers. As a percentage, it is 1.7%. This is about CB. So this is CB statistics. Actually, there are some consumers in LECO also. There are about 300 megawatt generation in LECO system also. So you see, out of 7 million consumers, that miracle is done by invisible rooftop solar by only 1.7% consumers. Then 98.3% consumers, the balanced consumers are there. So I have a solar system in my home. So I am very happy. So I don't get a bill. I get only the fixed charge, about 400 to 500 rupees. So I am a consumer of LECO system. I don't know, but I don't know whether my neighbors are happy about their electricity bill, because my neighbors, most of my neighbors are in this category, 98.3%. So they expect, the 98.3% consumers expect an affordable and equitable electricity price. Right, let's move to my next slide. New grid, in a conventional grid, you know that very simple, this system frequency operation, supply demand balancing. But in new grid, you can see there are in the consumer side as well. So then asynchronous generation and distributed and intermittent sources. The system frequency control center faces to big challenge when this asynchronous, distributed and intermittent sources are, the share of these sources are more. So that is what happened in these days, in Sundays and in holidays. Then for all these technical challenges, we have solutions. So it is not a challenge. We have solutions. So they are the solutions. So there are a lot of solutions. So I have mentioned some of them. The system, we should have a more smarter grid to handle this. That doesn't mean our present power system is not smart. But smartness of a grid is a relative measurement. So our system is also smart. There are a lot of smart features, SCADA systems, communication networks, and everything is there. But our system is not smart enough to handle present situation. But now our system control engineers and our management have managed the situation. But there is a challenge, because still this we have a target to go to 70%. Then we should have grid expansions. I explained you why we need grid expansions. And we need energy storage system, battery energy storage system, and pump storage system. And we need ramping generators like IC engines and gas turbines to go to our 70% target. And because of, we have to go to high share of renewable energy. So this, because of the share of firm energy power plant, those supply, primary regulation, recommend the share. The share will go down. We should have synthetic inertia as well. And load shifting, some students are here who study the energy systems know what is load shedding and load shifting. Then load shedding, sometimes load shedding should be done in contingency time to balance the frequency. Some immediate actions has taken by our system control center, and the management has taken some decisions and some initiatives to solve this problem. So I'll tell you some short-term and immediate actions we have taken to overcome this problem. One is this ongoing project. This is still under procurement stage. In the existing system control center, so we are going to implement a renewable energy control center. This renewable energy control center will communicate with large renewable energy power plant. Direct communication will be there, and it can control those power plants as well. The power plants above 1 megawatt. The distributed generation is handled by some distribution control centers. We have distribution control centers in 4 distribution divisions. So there's an ongoing project to enhance the facilities of these distribution control centers to handle these massive rooftop solar systems, and that the online real-time communication, the upgrading this system is going on. The real-time monitoring and prediction and forecasting of rooftop solar systems will be done, and that distributed control centers will communicate with the main server at the National System Control Center, Renewable Control Desk. So estimated cost of this project is about $40 million US. ADB has committed, I think, for one part they have committed. That is a part of my project, the renewable integration project, but it is handled by Deputy General Manager, System Control Center. So, and a total of, including the SCADA distribution control center, SCADA systems, and renewable centers, the total cost will be about $40 million US. In Sri Lanka rupees, it is about 12 billion rupees. It will come in 1 to 2 years, maybe 1.5 years, maybe. So this is the real-time monitoring of renewable energies in a particular day. So this is a Sunday. So here you don't see that other power plant. This is only non-conventional renewable energies. The large hydro power plants are also not there. This is only real-time monitoring of non-conventional renewable energy. Those are not dispatchable power plants. They are intermittent, and those power plants which having such problems and the technical issues, as I explained, this you can see this is July 27th. This is a Monday. From here to here, Sunday. From this dotted line beyond this deadline, it's a Monday. You can see this topmost share in orange color. They are ground-mounted solar. Rooftop solar are not here actually. So if it's wind, and light blue color are mini hydros. You can see in Saturday we had a considerable amount of wind and ground-mounted solar also. all these renewables are curtailed to accommodate this solar, invisible rooftop solar. So, control engineers, our 100 megawatt wind power plant in Mena also closed, switch off in Sundays and holidays to accommodate this invisible solar. And also, this ground-mounted solar, they are from the IPP power plants, private sector power plants. So most of these wind power plants also from private sector. Only 100 megawatt come from Sri Lanka, but 200 megawatts are private sector. Those power plants also curtailed. So, important thing is uh, actually these large-scale power plants provide low-cost energy because these power plants came with competitive tenders. They have competitive prices. Some solar power plants curtailing here, the price of solar power plants is less than, I know that, but in wind power plants also they are low. So the curtailing is done for low-cost renewable energies, right?